Welcome back to Differential Calculus. In this video, we're going to be talking about equations of lines. At this point in your mathematical careers, the idea of equations of lines should be straightforward. It should be old hat. You should be looking at this title and saying, wait, I know what this is. I already know how to deal with lines. If you are, you're in exactly the right place. If you aren't, this video is not going to be pleasant for you. Instead, I want to look at this from a slightly different perspective. The reason that you are so familiar with how to deal with lines and linear equations is that they are easy. In fact, they're easy to the point that there's not really a lot else we know how to do. Think back to the math classes you've taken previously. You learned how to graph lines. You learned how to solve linear equations. You started looking at polynomials. You learned how to turn a polynomial equation into a linear equation so that you could solve it. You learned how to use that to graph a polynomial. You learned how to turn a rational into a polynomial, which you could then turn into a linear equation and solve. You started studying trigonometry, and you learned that you can solve a linear equation, pretend that the trigonometric function is just a variable, solve for that, and then go about your business. So working with linear equations is what we know how to do. And everything else we know how to do in mathematics is make something look like it's a linear equation, work with it, and then go back and figure out what it means in the context of the more complicated thing. What we're going to be looking at in this video and the next couple that come after it is kind of a souped up version of just that. We're going to be taking expressions, taking functions that are very complicated, learning how to approximate them as though they were linear, at least in some small space, deal with that, and say it's close enough. This is how all computer numerical solving software works. And so there's the foundation. That's what we're going to be building on for most of this course, to be honest. But before we get there, I want to spend a little bit of time in this video reviewing the fundamentals. So let me get my head out of the way so we can do just that. There are a couple of different notations you can use for writing the equation of a line. The three most common I've listed here. Standard form, ax plus by equals c. We are not going to be touching, but I wanted to mention it just for the sake of completeness. Slope-intercept form, sometimes also called function form, is going to be our end goal, but point-slope form is the one that is going to be the most important to us in this course. Point-slope form is ideally designed for starting with a point and a slope and turning that into the equation of a line. We can use point-slope form to write the equation of the line through x naught, y naught with slope m. And I note here that this line is unique. Given a point, given a slope, there is exactly one line that fits those parameters. For the sake of time, I'm not going to justify that claim, but if you're interested, get in touch with me and I am happy to go into more detail on that. But this is going to be our prime objective. This is going to be what we are looking at throughout this semester. We are going to find a way, and the way will change a couple of times. We're going to find a way to get an initial point x naught, y naught. We're going to find a way to get a slope, and we're going to use those to write the equation of the line. It really is that simple. So for example, if I want to write the equation of the line with slope -5/3, which passes through the point 6, -7, I am going to not completely scroll the problem off the screen. I am going to start by writing down my point slope form, y minus y naught is equal to m times the quantity x minus x naught. I am going to note that my slope here is -5/3. I'm going to note from my point that x naught is 6, y naught is -7. I'm going to put those things into the formula to get y minus -7 is equal to -5/3 times x minus 6. And technically speaking, at this point I am done, but I did mention earlier in this video that we're generally going to be looking at talking about this line in slope-intercept form or in function form. So I'll do a little bit of algebra from here. To simplify the equation and write my equation of my line as y equals -5/3 x plus 3. All right. Even though the instructions don't always specify, as a general rule, it's almost always a good idea to write your equation of the line in slope-intercept form like this. The other thing I want to talk about in this video is the graph of a linear function. So I am now in Desmos, so you don't have to deal with my terrible drawing by hand, to talk a little bit about the equation. Get my head out of the way so you can see that behind me I was hiding. I am graphing here a generic y equals mx plus b. I have some parameters here for m and b. Of course, the slope changes how the line is tilted. If I have a slope larger than 1, I get a steeper line. If I have a slope between 0 and 1, I get a shallower line. A slope exactly 0 gives me a horizontal line. And then negative slopes are downward, but the same basic idea. B controls the y coordinate of the y-intercept. So if I plot out the point 0, comma b, you can see that it sits here on the graph. And as I move my value of b, that point is just tracking up and down on the y-axis. You've probably used tools much like that as your tools for graphing the equation of a line by hand, which is certainly something interesting, but not really the big idea we're looking for. Instead, as we have kind of through this whole thing, we're looking at the analysis in the other direction in this course. If I am looking at the graph of a line, can I figure out how to write the equation? Right? I can find the y-intercept, that's pretty easy to find. And I can find the slope of the line by looking at it as well. Thinking about the rise and run of the graph and thinking about how those things relate gives us the visual clue for the slope of the line. And again, you're probably more used to thinking about that the other way, but we can just as easily look at this and say, oh, in this graph, if I can't see all the equations behind me, let's see. It goes upward by about 1, 2, 3, 4-ish. It goes over by about 3-ish. So the slope is something in the ballpark of 4 or 4.5 divided by 3. We could move this and get an even larger triangle if we wanted to, which would give us a bigger picture, but that gets the point across. I think that's good enough for our purposes in this video. So that leaves me with a problem for you to try on your own. You will have to think back to your previous math courses, remember how to calculate a slope, and using that, I'd like you to write the equation of the line which passes through these 2 points, 2, 5, and 4, 1. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.